Welcome to my talk entitled Sugarcoating KANDYKORN. So we dive into a sophisticated macOS backdoor. So my name is Salim. I am currently a security research engineer at Elastic. I have previous working experience in red teaming and purple teaming, also pen testing. I am, unfortunately, a Flareon addict since 2018, like many of you, and I started working on it yesterday for this year's competition. So before starting, I would like to give a shout out to my team, my research team, so Colson and Ricardo, who gave a lot to this research. So yeah, first I would like to start with the agenda. So the background, we will answer questions how we detected the intrusion, when we detected it, and who we think the actor is. Next, we'll move on into a quick introduction. So we'll talk about how the intrusion happened and a quick execution flow of the whole chain. Then we'll dive into technical detail, so initial compromise, and then the next three binaries we discovered: sugarloader, hloader, and KANDYKORN. Some of them used custom network protocol. So we discovered like different versions that we will look into later. And then we'll finish up with some campaign intersection and some tooling for KANDYKORN, basically just to simulate it. Next, so we'll start with background. This research was published on November 1st, 2023 by Elastic. And we actually discovered this attack 2 weeks earlier on October 13. So how we discovered it was, in our telemetry, we have found, or we've seen two rules. So basically, the first one was suspicious execution of binary self-signed using code signing tool. And it was literally followed by a reflective binary load. Both these two rules, they are behavior rules, and all the Elastic rules can be found like on our Git repository if you want to look at it. And so yeah, these two rules were fired on Discord. So literally the legit path of Discord. So it was quite weird. So we traced back the execution, and we have found that file or a zip file was downloaded from Discord, and then it contained Python scripts, so it's a whole project, like really big project, and then it was executed by in the machine, in the macOS endpoint. So regarding the author, we have seen overlap with the Lazarus group throughout the techniques, network infrastructures, and some detection rules we have internally. So starting with the introduction. So how did this attack happen? So it was quite ingenious social engineering attack. So it basically, they targeted a blockchain engineer that was working for a cryptocurrency company. And they basically contacted him through a public Discord channel where developers hang around. And they sent him basically a zip file containing like Python project. It was like disguised as arbitrage bot for cryptocurrency, and it was like more of a coding challenge. So yeah, unfortunately, the engineer executed it, which led to this research and intrusion. So the intrusion involved multiple complex stages from scripts, loaders, droppers, and pretty full-fledged backdoor at the end. The malware's job had a super low detection rate, and one of them was using LLVM obfuscation, which made life a bit hard. And yeah, they used some custom communication protocol. As I said, we found two versions, so we've called them V1 and V2. So starting with the execution flow to give a better idea of what happened. So the attacker contacted the victim through public Discord. He sent him a zip file named crossplatformbridges.zip, And then the victim executed the man.py through PyCharm, and which led us to the load of a module that was part of the files called watcher.py, which is our state 0. So it was the initial thing. So watcher.py downloaded from a Google Drive link, testp.py, another script, which we call stage 1. Stage 1 led us to another script called finder_tools, which is still part of the stage 1, which was downloaded from a Google Drive link, like another one. And it was executed with a URL parameter that was from the author's infrastructure. Here start the real thing. So sugar loader, our first binary, stage 2, was downloaded on the machine under the name .sld. This stage 2 installed on the machine hloader, which acts as the persistence mechanism. So we will discuss about it later. And then hloader loaded again a sugar loader under another instance, .log. And yeah, there was some sugar loader does some reflective loading, quite interesting. And then it loads the final backdoor KANDYKORN. So starting with the initial access, we'll discuss about technical stuff. So yeah, as I said, it was executed, they executed main.py, hidden code inside watcher.py. So it's actually, it created a folder in the current directory and named _log. It downloaded testp.py to it, and then just imported it and executed it. We can see the files. It's pretty like elaborate, so it did look like some arbitrage bot, but yeah. Here, just a link, just a screenshot to show the Google Drive link inside. So it was not like encoded, hidden or something, like it was like there, like just a variable. And then we can see from telemetry, our telemetry, the HTTP GET request that happened through Python URL-lib. So here, finder tools were downloaded, and it was executed, I said, through a URL parameter, and it saved sugar loader under the user shared.sld. So moving on now with the sugar loader analysis, which was quite interesting as it was obfuscating other interesting stuff. So we are in this part right now. So what is sugar loader? So sugar loader is a packed native 64-bit binary. It was highly obfuscated, and it led to pretty much a zero virus total detection from October 14, since it was uploaded, until let's say 1 day or less after we published the blog post. It was run under 2 instances. So for the first one was for keeping a persistence on the machine, and the second one was just to execute the backdoor. So moving on, getting deeper into it, we looked for the start function, and it contained zeros, like no code, interesting code. But in the init function, which is like a section where it contains like C++ constructors, one of the functions contained the unpacking logic. It was LVM obfuscated. Like there was some, like a lot of dead code, which made it a bit hard to find where the unpacking instructions are. And it was pretty simple to unpack the code different ways, just hardware breakpoint where we know the code will be, or just dumping it or something. So yeah, I've put this meme where it says, all right, then keep your secrets, because why do I have to analyze or find out about the unpacking code when I have the main code of the sugar loader? But I think even if it kind of takes some time, I think it's important because it can give us some clues about the author, or maybe hints, or it can, like usually people just probably maybe compile with the same configuration of the compiler, and it can lead to finding new binaries of the same family, or new campaigns, like, or literally different malwares, which happened actually. So next, here from IDA screen, like assembly, we can see some junk instructions, opaque predicate, and direct jumps, and arithmetic obfuscation, a lot of it, so like it was full. So how can we solve this? So there are a lot of ways to do it. I tried to go through a fun way of doing it. So through emulation, for example. So we were able to emulate the code. Basically, we wanted to find the code blocks that are responsible for unpacking the main code. So first, of course, we have to handle some API calls, like memory allocate and some memory like protection stuff. So I have to do that. And then the goal was to first log the instruction pointer to a file, for example. And then it generated like 100 million instruction, which was quite a lot. So there is like a technique I have used in CTF, to be honest, in the past. So to basically visually look at plotting of the instruction pointer and then just look for patterns of loops. Basically, because we know the unpacking is going through a big loop where it's gonna parse like a huge amount of data, which is the impact code. So we know like at some point there will be a loop that is gonna be repeating itself like forever, for a certain time. So that's the idea. So a quick diagram how it looks. So here we have a diagram of, or a graph, or 100,000 executed instructions. It looks a bit terrible, but we've divided it into like chunks. Like let's say we start from 0 to 20K, and then 20K to 40K, and then we have like, let's say 10 graphs, and then we look at each one of them. So here is from 0 to 4,000, which still we can see some loops. Basically, we can at least now find the loops that are executed once and then not anymore, which can be the dead loops from LLVM and etc. So here we have found a graph that was quite interesting because it was pretty much at the end, and it was kept repeating itself. Like it was like this for some time, like for a large amount of executed instructions. And zooming in it, we can start to see the pattern that is just keep repeating itself. So what we can do is just isolate these instructions, get them, and just read them. It was like 2,000 instructions. You just look at them, and you will easily find the code that is doing the unpacking. So yeah, so I think this is one of the techniques that you can do multiple ones to get the same results, I guess. But it saves time, I think, and then we avoided dead loops and junk codes, etc. So yeah, let's go back to Sugar Loader. So we found two parts to it. First one was CRC2 check of all the sections, and the second one was like unpacking method resembling UPX, and building taking from some of those instructions. We have found like new recent binaries, like from MacOS binaries that had literally the same packer and the same LVM obfuscation. So we discovered like other basically sugar loader samples plus other family that we'll discuss a bit later. So what it does, it first has two modes. So it either loads configuration from command line, so you give it IP and port, or from a file. So the file is library cache com apple safari.ck, and yeah, if it does not exist and you give it the parameter of the C2, it will just create it, and that's it. It does encrypt the configuration file with an RC4 key, 64-byte long, which is hard-coded in the sample, and it randomly generates a random client ID. It was seeded with the current time. It just sent it to the C2 for yeah. So next, what it does exactly, it downloads a macOS binary from the C2, and then this is the important part. So it reflectively loads it into memory, like Usually with reflection, I see it on Windows usually, but it was interesting because the author have been using this technique in the past, like that. I've seen it in other research, etc. So it was quite interesting. So they use an create object file image from memory and an link module to do that. It was quite simple. And we have seen that it drops a file called appname, which is hloader, the second binary, under discord.app. But at this time, it's still appname. So moving on with hloader. So it's self-signed Swift 64 binary. It was super small. The code base is like nothing. It's basically the persistence mechanism. It's literally the persistence mechanism through execution of flow hijacking. So we took the name from the signing. So from the identifier, we have found hloader, so we named it hloader. And what it does is hloader then is named to Discord. So basically, the real path of Discord, and then the original Discord is named .log. So what happens is, as I said about the execution flow hijacking, so basically each time the machine is booted or Discord is started, it does the following. Like it first renamed itself. Now it's called named Discord. So it names itself macOS.tmp. This one is hloader, of course. And then it renames .log, which is benign Discord, to Discord. It executes Discord, and then it also executes Sugarloader, like the second instance I spoke about, under the name .log with the task, launch, and return error. And when it does that, it basically renames the file back. So just interesting persistence mechanism through hijacking. So moving on with KANDYKORN, which is the meat of this research. So we have full-fledged backdoor. It was compiled with debug mode, which made life easy. And yeah, it used the same stuff like Sugarloader, like the configuration and network protocol, literally the same. It contained the same key inside, hard-coded, etc. It reports error code to the C2. This stuff is important. It's super important because we can keep track. We can keep track of the author. Like if they reuse the same error codes in other samples, at least we have like small percentage of knowing that it might be this actor. And it handles like 16 commands in total, so pretty versatile, and it has proxy settings that it can handle, that it takes from the configuration, actually. So here we can see in the screenshot a seek structure of the configs that we will go through. So the size is 488 byte in decimal, and it has like some fields that generate a computer ID or client ID. So that is generated at runtime, either by Sugarloader or KANDYKORN. It has the URLs, like 2 URLs and 2 IPs. So like if something happens, at least they have like 4 backups. It has like the proxy settings in there and the sleep interval for beaconing. So first it tries to connect to the URLs, and then it moves on the IPs if it fails to do that. So 2 and then 2. So the error code table in here, of course 0 for success. We have, like, if something happens, network related, there is a code for it. If a file opening error is found, and like if opening a zip file is fails, or if the command is not handled, and the last one is an error for writing to PTI because it creates a reverse backdoor at some point. So here's the command table, 16 in total, starting from D1, the command ID, to E0. Pretty versatile. They have like custom, like collect system information to uploading new configuration, downloading files, and yeah, pretty much. They have also like an interesting file wiping method. So we go through some of them, and yeah, now we talk about the KANDYKORN capabilities. So as I said, because we have the debug mode, they enable compiled the debug mode. We have the symbols, like the function commands names. So yeah, the first one I would like to talk about is RESP basic info. It collects just system information like host name, username, product version, build version, the IP address, and the current image path of the current process. The next one is RESP file dir. So it lists content of directory. It was pretty similar to ls.al, but they don't do it through a command line. They have like a parser just to avoid executing commands on the machine, but they just use APIs, macOS APIs. So next we have a command to list running processes. Same idea, they just use APIs. PID, it collects PID, UID, and create time of all the running processes. And then we have command execution. So they do it in like they have three separate commands. First one, create a reverse shell, and then they have a command to send, and then another command to receive the output. So about the file wipe, so basically they first override the content with zeros, and then they delete the file. So yeah, just a measure to make forensics pretty difficult, which is interesting. And then we have like just simple like sig kill. It take like PID and then just sig kill with a signal any process. Next we have like some configuration, upload or download. So here, because the binary does not create, does not modify the proxy settings, so it's fed through this command. Moving on with the network protocol, so it was basically basic. Now we will be talking about the V1 protocol. So basically we found two versions of the same KANDYKORN, and the difference was only on the communication protocol, basically. So both of them had like similar stuff. So handshake, client ID, send client ID, and then send payload or command. So they used, for the V1, they used a hard-coded key for the RC4 encryption. It was the same that is used for encrypting the configuration file. So basically, KANDYKORN generates a random value, send it to the server. Server sends a C2 nonce to the KANDYKORN. KANDYKORN do some calculation with two values. It sends a challenge. The server validates the challenge and then send C2 validation, which is like a 4-byte or D-word magic value. And then KANDYKORN is like, okay, and then connection is established. Now just wait for commands or payloads in case of Sugarloader because they use the same protocol. Here is the Wireshark capture. And then we can now talk about the V2 protocol. So it's different, super different. So they don't use the hard-coded key, use it for the encrypting the configuration. So they basically generate 400 in hexadecimal random sequence, and then they send it to the server. Basically, this sequence contains at some indexes a new RC4 key and a check sequence, which has like 100 in hexadecimal size. So basically, KANDYKORN sends it to the server. Server extracts those needed information, and then it encrypts the check sequence with the RC4 key, and then send it to KANDYKORN. So KANDYKORN will now receive the encrypted check sequence. It will try to decrypt it and compare it with what we send. So if it's okay, the connection is established, so the handshake is done, and then the rest is the same. Client send client ID and then receive commands. So for some combined intersection, so here we have diamond model, but I don't think I have too much time to go through it. It can be found on the blog post. So for combined intersection, we have seen some TLS certificate anomaly. So it starts with TP global.xyz. It used, so this one was the one that downloaded the Sugarloader. So it used the certificate subject CN of this bitscrunch.linkpc.net, which was linked in the past with Lazarus. Sentinel-1 discovered new Lure zip files, pretty much the same, and they contained the V2 version. We have seen Rust bucket disguised as a PDF viewer. It was already reported, but we have found it through the Yara rule we created through when we analyzed the package. So it was literally the same packer, and Rust bucket was from the same actor. And then we have seen some recruitment rules in Reddit. Some user reported that they've been contacted by some recruiter to solve a coding challenge. Pretty much the same stuff. So finally, I would like to share that we've created a tool for simulating KANDYKORN in a real-world attack scenario, basically to build and validate detection rules. It can be found on this link. You can find it later in the slides. And yeah, I think that's it. Thanks a lot.